So we are going to move through some information about the energy chapters again today. And we're going to continue with the non-renewable energy sources first, and then we should be moving towards renewables. We talked a little bit about oil last time. We're going to continue talking about oil. And you're all familiar with the concept of oil that we get from oil wells, correct? Are you familiar with the concept that we can get oil from sand and from rocks? It's important to be able to see these for this slide. So what you see in the top picture are tar sands. What you see in the bottom picture are oil shale. These contain oil products. Do they look like oil? How much processing do you think it takes to get oil from them? Pretty good amount. The tar sands do contain heavy oils. They are found between rocks of sandstone deposits, and they contain bitumen, which is similar to a coal type. They're found in Canada in many places, very rich deposits in Alberta, and it's one of the places where they are being processed into oil, and some of that is being shipped to refineries in the United States. The oil shale is more common in the U.S. As a matter of fact, we have a lot of oil shale available. It does contain keratin, which is an oil product, and you can process it into oil. So you can take a rock and get some oil out of it. There's a lot of processing that has to happen. There's a lot of energy invested into it in order for this to happen. And then once you make the oil is going to need to be refined, and it may contain some concentrations of pollutants that would be different from a regular oil supply. The reserves of these are large. The amount of energy that goes into extracting them is also large. Do you think this is something that we should be going after as a possible energy source? We can get oil from it.
But it's not renewable either.
It is not renewable as well. It does create some level of pollution. It does deal with some land destruction.
I know for the tar sands in Canada, there's a lot of land degradation also related to the indigenous peoples. Like that's their land, and then a lot of it's destroyed.
Yes. Yeah, there's a massive dispute in Canada about Native American people groups and who owns the tar sand areas, and then who should profit from them. Any of you think that instead of extracting oil from things like this, we should be spending the money on other types of energy sources? Yeah? Also, at some point in time, this becomes more expensive to get the oil out of than the oil that it can generate. We're not there yet, but there is a time period where we will have tapped into all of the easy to get tar sands and easy to get oil shale, and then but then we have some questions about how long are the oil supplies going to last anyway. Have any of you heard estimates of how long energy supplies will last, or oil supplies will last?
Isn't it supposed to run out like before 2080?
Before 2080? Maybe. Part of this is going to depend upon how much oil we use, because some of the metrics that people use for predicting when we'll run out of oil include using oil at the same rate that we're using it today, some of them higher rates than we're using it today, and we're not convinced we're necessarily going to use it at higher rates than we are today, because lots of people are cutting back on their oil use. But oil in the United States is a big deal. Best numbers I have from this are from 2010, but in 2010 we produced slightly less than 10% of the oil in the world. What percentage of the oil do you think that we used? So we produced about 9–10%. What percentage of oil did we use? Not of that, of the worldwide production.
About 40%.
Wow, you think we're really bad? No.
15.
About 20 to 25% is what we used. It was like around 23%. So we produced 9–10, used 23%. So we're using more oil than we have here available to us. About 2%, 2% of the worldwide proven reserves of oil can be found in the United States. And our oil production has been steadily declining in the US. It did start increasing slightly in 2008 with the introduction of fracking. But even the majority of the oil that is still left in the United States that could be taken and utilized isn't going to last us very long. You've all probably heard that there's oil reserves in Alaska, correct? The Alaska North Slope. Getting that oil is going to be difficult. Even if we only use the oil there for our own work in the United States, it will last us 6 whole months. The Arctic National Wildlife Refuge, we expect the amount of oil that's in that could last us between 1 and 2 years. It will take 10 to 20 years to get all of the oil from it, and the maximum money that we would save as consumers would be about 5 to 6 cents per gallon of gasoline. And that's when you start to wonder, is 5 or 6 cents per gallon of gasoline worth the environmental cost of what could happen to the populations living there? And sometimes I think that is the question we should be asking. Oftentimes when we talk about whether or not we should get oil, the questions that people are asking are, well, maybe we should drive less, or what is this all about climate change? But it's really not in this question about those things. It's about the health of the land and the health of the animals that get to live there and call that place home. Because there's a big difference between thinking, if we get that oil, my cost of a gallon of gasoline is going to be 40 cents, which is, I think, what people are thinking in their head. Gas is going to cost nothing if we get that, or it's going to cost a lot less to heat my house. But when they hear that it's only 5 to 6 cents less per gallon, but in turn, the moose populations, the bird populations are going to be dramatically impacted, that changes their perspective. And in environmental work, in biological work, sometimes that's what we need to do. We need to change the conversation so that it's really about nature, that it's really about science, that it's something that people can connect with. Many of you said what you loved about Leopold was how he wrote things, and he made you want to be there, and he made you want to experience nature in the way that he did, or at least made you think about nature in the way that he did. If everybody had to read that book, would they think about drilling in the Arctic National Wildlife Refuge differently? I think so. How long exactly an oil supply is going to last us depends on a whole host of different factors, mainly including things like demand. How much do we use? Technology. Do we have other ways to do things that will use less oil? Or can we do more by using less? Our rate of removal. Because sometimes when there is more of something available, we tend to use more of it. We don't think about this as much necessarily with oil, but let's imagine that you had really fabulous food in the cafeteria. Would people put more and more on their plates than they intend to eat? And a lot of it would end up in the trash, right? That's the same concept here, that when there's a whole lot of something available, sometimes people are going to use it up faster. So if the cafeteria had much better food, even if people weren't eating it, it will be removed from the trays much faster. Some of it would be put to waste, just like energy is. The production cost also matter. If it costs more to get oil, we tend to use less. The sale price, the politics matter. I mentioned last time that OPEC owns a lot of the oil reserves, and we're not on the best terms with some of those countries, so it may make it difficult for us to get oil in the future. And also our exploration success. So I did my postdoc work on paleoclimate construction. I worked on sediments from the Antarctic, well, from the Southern Ocean, so the ocean around Antarctica. And they were about 6 million years old, the sediments that I worked on, which really actually sounds far more impressive than it was most days. I did not get to go to Antarctica and get them. And I think I shocked Sarah when I mentioned where they came from the other day. Remember where I said they came from? Oh, the oil industry.
Oh.
So one of the things the oil industry does, one of the good things the oil industry does, is that as they go around the world looking for places where they can get oil, especially from under the ocean, they donate the excess sediment that they collect, the excess sediment cores, sometimes in their entirety, to research scientists. This was the ocean drilling program. Now it's called the International Ocean Drilling Program, I think. And it's an amazing way that we get to understand what sediment from the past is like. So when they tap down and they do a core, they pull out the sediments, they look for some indicators that there's oil there. And if there is, they may put in a test well and see what happens. If there's not, they're not going to reuse that area, but they will donate the sediments that they've pulled up to scientific research so that we can understand the ocean better. That is a good thing that they do. However, their exploration success is not always successful. Or their exploration is not always successful. So they may put down a whole bunch of test areas and find that there's no place where they can get oil in an area. But they do at least have some working with science in that. And the oil industry does employ a lot of scientists. It is important that you know that. One of the guys I went to grad school with works for the oil industry. He dropped out of grad school when he was just finishing up his thesis because he was offered a job with the oil industry. And it was well into the 6-figure job offer, and he was like, the stress of finishing my thesis is not worth it. I'm gone. He makes more than everyone I went to grad school with, I think, now. Sometimes people tell him he sold his soul, but he makes a lot of money.
What are they doing with that? Like, is he like judging environmental impacts?
His job is actually in oil exploration. He's a geologist.
Okay.
And it was finding the areas where you might be able to find oil deposits and looking at the geology of areas. I don't know how many people are employed looking at environmental impacts. There are some.
Mm-hmm.
There are some that even work on like the offshore drilling towers,
Mm-hmm.
where you have to have people that are going to be able to inspect and make sure about your impacts. But there are jobs in the oil industry for scientists.
Yeah.
You may not think of it as the natural fit for a scientist, but there's good money to be made. And Exxon? How many of you, when you hear the word Exxon, think of oil spills, the Exxon Valdez, everything like that? They are actually employing people working on developing alternative energy sources, including the use of algae and algal byproducts as a fuel source. So you should know that some of these organizations that you think of as only doing bad are in fact working now on realizing that they need to do something else. Not because they think oil is bad, but because they recognize oil is not sustainable as a long-term business model. So it is a business choice, perhaps, rather than an ethical choice to go in a different direction. But they've also released, and we'll talk about this in chapter 13, their own statements regarding climate change and the role that their companies have played in it. So it is interesting that the oil companies are trying to find other ways to make amends for what has happened with oil spills, but also to find a new energy source. And this shows you what would come from the Arctic refuge over 50 years, as opposed to the oil consumption. In case you know people that tell you, oh no, we can totally fill all of our needs from this, and you want a graphic to show them, this might be helpful. It's not, in my opinion, worth it for that. It's a drop in the bucket, literally. There are some massive environmental costs to our use of oil. It has serious, serious effects on the environment. Some of this, most of this, I imagine you know. So, air pollution. Unfortunately, when our cars burn oil, or when other processes that we use burn oil, it does not entirely combust. We know this. Our systems are built around it. Your car is designed in a way to reduce the amount of pollutants coming through and to help with the best combustion possible. But you are going to have byproducts in the smoke. It will contain carbon dioxide, but there are other chemicals that are also going to be contained as well in air pollution. And chapter 12 is about air pollution, so we'll spend more time on this then. But you get nitrous oxide, or you get carbon dioxide and other chemicals that will get up into the air. They cause what is called photochemical smog. So that's when the light and the chemicals that are in the atmosphere react together and they form a fog-like structure that, if it's high in acids, can actually etch things, but that it makes it very difficult for many of us to breathe. It gives a red-brown color. We've found that areas with high photochemical smog have decreased plant growth, and those with asthma, bronchitis, emphysema tend to not breathe as well in areas with high photochemical smog. Acid deposition is a massive problem. This picture is a great demonstration of it. This is from the Appalachian Mountains in North Carolina, and it's looking at an area that used to be covered in spruce trees, which are sensitive to acid rain. Oil spills and leaks. Oh, they get publicity. The large ones, at least. We're going to come back to oil spills in a little bit, but it is important that you know, while the large oil spills are horrible in the fact that they have massive environmental consequences, the smaller oil spills, the small constant leaks, actually leak more oil than do our large spills that you hear about. Carbon dioxide is increased that is connected to global climate change. And the use of oil accounts for 43% of all carbon dioxide released by human activities from fossil fuel. It's a problem. And then there's the impacts of oil just to get it out of the ground. Land degradation, water pollution, sediment pollution. What's going on in these pictures? Can anyone take a guess? What's happening in the top one? Photochemical smog. This is over Santiago, Chile. It's caused by gasoline and diesel fuel. How about in that picture? That's the BP Deepwater Horizon drilling platform on fire. I'm sure you're all familiar with that one. Happened in 2010. And over here, what do we have? Brown pelican who've been caught in an oil spill. What soap do we use to get oil off of birds and mammals that have been caught in oil spills? Blue Dawn. Only the blue one. If you're interested, and I should be able to still find them, there is a video series about how they, or a number of different videos about how they stumbled upon Dawn as being like the safe thing for removing oil from birds and mammals, and why they picked it over other things. Interestingly enough, it was a last-ditch effort when they discovered it, they tried all of these other surfactants and things that should be safe, that didn't remove the oil. Then they found ones that removed the oil but were really harmful to the skin. And then one of the people was like, well, when I use the Dawn at home washing my dishes, my hands are still fine and the oil's off of all my pots and pans. It's worth a shot, right? And it worked. It was the only dish soap that they tested that actually worked. So it is serious when it says it does support wildlife. And they will donate when there is a massive spill so that there's something to clean the wildlife. We do have some problems that are related to our use of the heavier oils. Those heavy oils, the heavy oils being the tar sand oils and the oil shales. Canada right now is our primary producer because they are rich in tar sands. Oil shale production, you're starting to hear a little bit about in the United States, but it is not a big industry yet simply because it produces so much waste and it is so expensive to do. In order to get the oil tar, tar sands, you frequently have to first do some clear cutting in an area where it is. So you cut down the forests. Sometimes you have to divert the river flow because you don't want water flowing over this oil-rich sand. And then they start doing strip mining to get through the rocks in order to pull up the tar sands. Massive damage to forests and rivers. But there's a low net energy yield associated with this. And it produces 82% more carbon dioxide than the conventional oil for the same amount burned. So it produces less energy and it creates more carbon dioxide pollution. Oil shale is expected to produce about 25 to 50% more carbon dioxide than conventional oil, depending upon the type you have. So oil shale is better than tar sand oil, but it's actually more difficult to get. And both of these are energetically expensive to harvest. And this is in fact what it may look like. This is the tar sands project in Alberta, Canada. How much impact do you think is happening here? So if we have to choose, how many of you would rather have solar panels or windmills there? And, you know, instead of all that water for cleaning and processes, maybe a hydroelectric dam if we could have one too? Do you think it would be a better investment of money for the long term as well? Because that's another part of this is, sure, we are degrading the land. Absolutely. Might the land recover? It could. But the investment cost in this is also very expensive. If we would spend the same money investing in building solar or wind, the electricity generated from them would last a lot longer. And if the electricity lasted longer and we had more electricity to power our homes and our businesses, then maybe the oil reserves that we have would in fact last longer. Because sometimes it's really about diverting how we use power in order to make what we have last a lot longer. We're going to move on to natural gas. Methane. So natural gas is methane, it's CH4. It is a combustible gas. It provides about a quarter of the U.S. energy need. Does anyone know if their home is heated by natural gas? A couple of you? Do any of you have a gas oven, gas stove as opposed to electric? Okay. So we use natural gas at my house for heating. It's the stove, it's oven, water heater, everything is natural gas. It's easy to transport in pipelines. Potentially sometimes easier than oil to transport in pipelines. Natural gas can be transported via ship. That is a little bit more difficult. We'll see that in a moment. But what happens is the gas is combusted, it's burned. And as it burns, it produces a lot of steam. This is used to turn a turbine. Turbine is attached to larger machinery, and the turning of the turbine produces electricity. Natural gas is found in a relatively short supply. Having said that, we strongly believe the natural gas deposits we have will outlast the deposits of oil that we do have. It is formed above the oil deposits in the ground, so even in areas where the oil will be hard to get out, the natural gas might be something that we could remove from the ground surface. It burns very, very cleanly. Because of this, it is suggested as our best transition fuel as we go from fossil fuels towards renewable energy sources. It can be used to generate electricity. It can be compressed and made into an automobile fuel. You can easily use it to heat your home, to power businesses. So it can do much of what oil is capable of doing. It's transported in pipelines, yes. And it is sometimes transported as a liquid, as in liquefied petroleum gas, that LPG. And when it's like that, it is kept in tanks. It can also be kept as liquefied natural gas. This is what we usually do when we're transporting it. And then as soon as you get it where it's going, you take it back from the liquid to the gas form. So it can be converted into a liquid and then converted back. Russia has 24% of the natural gas reserves worldwide. Iran has 16, Qatar's 14, and we have about 4 to 5%. That's more than double the amount of oil we have, though. This is a turbine. So this is one of the things that would be turning in order to create our electricity. But there are some problems with natural gas. It does have the lowest environmental impact of our fossil fuels, so we got a good thing going on here. It releases less carbon dioxide per unit energy than oil. That's good. It has lower levels of land degradation associated with removing it. That's great. It produces less water and less air pollution. Also good. Even with fracking, it is much easier and cleaner to remove than regular oil deposits are. So that's good too. Liquefied natural gas is easier to transport than natural gas itself. But we do lose some energy as we take it from a gas form to a liquid and then liberate it back to a gas. If these tanks start to leak in transit, it does pose a pretty big problem, though, because when they're stored as a liquid form and they're in tankers like you see here, it could be contamination of petroleum product with the ocean. But we also have a big concern. If a tanker of these were to catch fire, just as an oil tanker would, you're going to have a pretty big fire. But unlike oil, the liquefied petroleum gas, it's going to start to expand as it's also going pretty quickly. And it is going to be a much more massive fire and harder to put out than it would be if it were oil, simply because of the higher flash point and everything that we're dealing with here. So these can create fireball situations if they do catch fire. So we tend to be very cautious with them. And you also are going to potentially have things that reduce static electricity in areas where they are kept. Fracking. What do you know about fracking?
Correct me if I'm wrong, isn't it the insertion of various materials, whether they're explosive or liquids, into parts of the Earth's crust in order to cause an expansion in the ground, which will then go release some natural gas that's kept there?
So we're going to dig some sort of a hole, long, deep hole. We're going to shoot some stuff down, and we're going to make some other stuff come back up. basics of fracking, right? Very, very basic fracking here. We're going to create a hole. We're going to send water and other things down into it. And generally speaking, we're then going to suck that same liquid back up. And as we do, we're going to pull other things with it. Do any of you automatically have like a sense of dread about that concept? What do you think happens to the ground surface when we put things into it under pressure? It's going to crack in some places, right? And that's part of this. Fracking is going to need cracking to occur in order to liberate the gas and the oil products nearby. Do any of you have any long-term concerns regarding the ground's surface and structure, though? Fracking does cause earthquakes. There's a concern in some areas. Let's imagine we did this right next to your house. What do you think that would do to your foundation of your home? This is usually done pretty deep, so that's not a concern. But just think about what it might do to a foundation of a house or a business. Might make you wonder what is it going to do to the underlying rock structures. And that's something we don't have a lot of data about because this is a new technology. So we don't know what the impacts are going to be long-term on the structural integrity of things. Fracking has allowed us to get higher production of natural gas. The materials that we put into the water to liberate the gas, to cause the cracking, to get the oil out, are not well studied if they are studied at all. We know that this takes a lot of water to do well. And if we're concerned about water, that becomes a problem because the water, when it comes back out, is highly contaminated. And it must be decontaminated before it can be used again. It produces a lot of wastewater. That wastewater is highly toxic. It contains benzene and radium as well as cancer-causing agents. One fracked well can produce more than 1 million gallons of wastewater containing these compounds. The 2000 U.S. Energy Policy Act did exempt the fracking industry from wastewater laws. I'm not going to tell you to blame Congress for that. I'm going to tell you to blame lobbyists for that one if you're looking for somebody to blame. They are the ones who got it added into the bill. The question becomes, what do you then do with all that water? Well, one of the policies enacting in a few areas is that you're just going to inject it back down into the ground someplace else because we all know that the ground cleans water, so it should work. So then we're injecting water in multiple locations, which could contaminate aquifers. It could contaminate wells. It could contaminate the groundwater. And in Ohio and Oklahoma and Texas, in those 3 states, in a 3-week time period in November of 2013, there were 16 earthquakes. All in areas that had recently started fracking. One of the recent articles I saw said that in one area that they've started fracking, they now get sometimes 200 earthquake tremors per year. Yes, we need power. Yes, we need energy. But is the damage actually worth it? And one of the other things that happens from this is there's a lot of methane emission. So we can take a lot of natural gas from them, but a lot of natural gas is also lost. So are we actually getting an amount that's worth keeping? What do you think? Is fracking worth it?
I feel like it's better than oil, but the money is still better spent by investing in renewable sources. So unless there's like a reason that no renewable source will work in that area, like maybe, you know, that would be a situation in which it would be better, but I don't know if that's...
How many of you have ever tried to get, it could be your parents, it could be your grandparents, to do something totally differently? Or like an aunt or an uncle, or even for that matter, like an older sibling or a cousin, and they're like, yeah, that is so not the way we do it. Like, oh, let's go with a really simple one. Using Uber as opposed to calling a taxi. We don't do that. Like, that's not what they're used to, right? I mean, at some point in time, somebody bought my grandmother a computer, and she was like, what would I use that for? It's a nice paperweight. Don't need to know how to use that. That's kind of that was her take on it. And no, she never did in fact use it. You might be wondering what I'm getting at with this, but it's this idea of changing energy technologies, changing any technology is scary to people. It's unnerving. We're used to the things that we know how to use. So the idea of installing solar panels in everybody's house might not be something they want, because maybe there's a fear associated with it, the fear of doing something new. We see that in psychology concerns, we see that in education all the time, but it's also true about how we do business and how we deal with energy technologies, because you don't want to move out of your comfort zone. What if I said to you today, you should go out and buy a solar paneled car, and you'll never use electricity, you'll never use energy again other than solar to drive your car? How many of you will be really okay with that? How many of you are going to be like, but what happens on a cloudy day? And what if it's raining? And what if there's a cloud that comes over my car, and you have all these questions and all these concerns, right? And we don't have enough answers for them yet. That's kind of where we are in energy technology today, is we can't quite make the jump. I'm sorry, this one is actually natural gas being burned off of a deposit. This is an area where we can't trap all the natural gas, so we're combusting it, so it causes less air pollution. But if we could trap some of that, we would get more from our usage. In case you weren't sure, we're moving on to coal. Coal is created under very high heats, very high pressures. It is a carbon material that has been altered into a rock-like status. It really is a rock. Coal is made of plant material. It's about 200 to 350 million year old plant material. We burn it. It creates heat. The heat turns the turbines create electricity. We get power. It works. The Industrial Revolution was driven by coal. We expect to have enough coal reserves to last at least 200 years. This is going to last us a pretty long time. It produces 40% of the world's electricity, or 41%. Apparently, depending, we'll go with 40%, that's close enough. 45% of the energy in the United States and about 80% of the energy in China. It's abundant. The US has almost 30% of the world's coal supply. Russia and China also have a significant amount. The reason that coal is linked to the Industrial Revolution is that coal was used to make iron and steel and other metal products as we moved through the Industrial Revolution. Coal mining is problematic. It does disturb the land. It causes erosion. It causes acid mine drainage, deforestation, and then land subsidence. Subsidence is the idea that the land is going to sink, usually because something has been removed from underneath of it. When we talk about water, we'll talk about subsidence there. But here what's happening is I've mined into an area. I've taken out this coal from down here. The land up here is eventually going to start to compact and sink. Coal is a problem when we look at pollution. It produces carbon dioxide, sulfur dioxide, nitrogen dioxide, particulate matter, mercury, all from combustion. It remains in the atmosphere. It causes acid rain. It causes acid precipitation. We've been able to control sulfur dioxides, but not the others, with scrubbers installed. Think of them as filters, and filters installed into smokestacks where this is burned. We usually use coal that contains less sulfur. And if we control the temperature at which things combust, we can change the ratios of the pollutants that we make. But reducing emissions even lower is difficult and it becomes expensive. You can change into what's called a fluidized bed combustion, which reduces the amount of carbon dioxide and sulfur oxides coming out of the system. Then there's the idea of clean coal. What do you know about clean coal? Who thinks clean coal is real? I got no one. Okay. So clean coal works in combusting it in a way where it produces less pollution. And usually where clean coal is happening, they're doing something like planting more trees and things in order to pull in the carbon dioxide. Then there's coal gasification, where you take the coal and you make natural gas out of it. And then you can have coal liquefaction, where you...
Does it take a lot of energy to turn into gas and liquid?
Yes, it takes some level of energy to get there. This is showing you the process of going from peat to different types of coal. The coal that we want to burn is the anthracite. That's what the U.S. has a lot of deposits of. Worldwide bituminous, there's a lot of deposits of. It is widely used. It does contain a high amount of sulfur, so that one does produce more pollution. We tend to do anthracite in the U.S. as we burn to keep up with our air pollution standards. And this is showing you the concept of a place that utilizes coal in order to create energy. You'll notice that it turns the turbine, generates power, passes that to the people. Some waste heat is given off. Some of it is put to the atmosphere. A lot of times what they're trying to do now is retrofit these buildings so that waste heat is captured and used to heat the building, to heat their water and things like that. So they're trying to find a way to keep that heat from being waste. Ash disposal is a problem because once you burn coal, it doesn't burn completely, unlike natural gas, so you do have a waste product left that you need to get rid of elsewhere. Coal is our most abundant fossil fuel. It is, so it should be something we could use easily. There's a lot of problems. It's difficult to get from the environment. Mining destroys the land. There's strip mining, which is like surface mining, where you just take everything off the top and start going down to get it. This works well if your coal is not deeply buried, but it creates a lot of waste rock. Then we have mountaintop removal, where you use explosives to blow off the top of a mountain. How well do you think that does in creating a lot of waste? A whole lot. And then it generally means that the valley next to it starts to become filled with waste, which is usually where people live, so it produces health hazards. Subsurface mining is deep underground. This is where you hear about the miners getting trapped in coal mining. Miners are at risk for disease. There's concerns about explosions, fires, cave-ins. So those are not great for the land, but they're really not great for the people mining in them. Mining does produce coal, but it also produces a byproduct called sludge. And that sludge is pollutants that are collected. They're held in ponds. The water becomes very, very toxic where it is. The water should evaporate out, leaving behind a more concentrated sludge over time. If this is an area with a water table aquifer where the water is right underneath and there's no cap between it, the toxins can start to seep into the groundwater, which can then contaminate wells. There have been instances where these sludge ponds have ruptured or overflowed that has caused serious water pollution. It's our largest source of air pollution of our fossil fuels. Carbon dioxide, nitrous oxides, sulfur oxides, mercury, particulate matter. All of that is harmful to the environment, but all of that is harmful to people. Several thousand people every year die from pollution related to coal burning. And it produces a lot of carbon dioxide. How much more carbon dioxide do you think coal produces than burning oil?
Twice.
3 times. How much more than natural gas? 5 times. How much more than nuclear power? 17 times. 25% of the CO2 emissions that are generated by humans are generated from coal burning. 40% of that is generated in the United States. And this is what coal mining can look like. It's very disruptive to the environment. This is what burning coal can look like. Still not too good. It can be cleaned. You have heard about coal, clean coal. It is a thing, but it's expensive and it's complex, and it means that we install these pollution control devices inside of the smokestacks. This is a concept dealing with retrofitting the systems. And the question becomes, is clean coal really a myth, or have we just made the burning cleaner? So the coal itself isn't any cleaner. It's the process, unless you're using anthracite instead of the bituminous. But it's the process through which we release the exhaust that we've made cleaner. The environmental costs of any of these are not added into the actual cost of electricity or gallon of gasoline or any of that thing. We expect that if we started to add in the environmental cost of coal, coal suddenly becomes the most expensive fuel source. Right now, it seems to be the least expensive fuel source, so people go with it. It is considered by many to be the world's dirtiest fuel source. You're going to tell me that the dirtiest is actually nuclear energy, aren't you? Nuclear fission is our source of energy. Energy is released in a nuclear reactor. Radioisotopes produce alpha, beta, and gamma radiation as they decay. Nuclear power relies on fission, our splitting of atoms via radiation. Radium-235 is what we tend to use, and it will react in the reactor core of a nuclear reactor. You're going to have vessels there to contain the heat. You're going to use the heat in order to turn these turbines, and you'll need a cooling system to keep everything cool. But we can't really control nuclear energy. It's intense, and it is hard to control. We can start the process, but we cannot stop the process of fission. Nuclear waste is really, really difficult to dispose of. And the biggest concern, according to your textbook, is it makes us a target for terrorists. Because how else do you get nuclear material? Easily. Well, the easiest way to get it is to just take over a nuclear plant. I think your book overblows this as a concept a bit, but they are very concerned about the U.S. being a terrorist target, or our nuclear power plants being a terrorist target. It is true that the meltdown of a reactor will send radiation out all over an area and will cause a lot of problems. And we'll talk more about that next time. We are not going to have a discussion next time. We're going to move our discussion. I was going to put it Friday. We're going to move our discussion to next Wednesday so that everybody is here for that. Does that sound okay? We will have an energy debate. I'll give you the instructions about that next. But this is an image looking at a nuclear reactor. It's a water-cooled nuclear reactor, because even in nuclear power, we're going to be creating a lot more energy than we need. Most of the energy, well, energy that we can't use at least, and most of the energy that we can't use is going to be lost through heat energy. But it is really, really hot. And you probably learned in chemistry about the concept of water as our best solvent, right? Water is also fabulous at holding on to heat. So we use water to cool down the nuclear reactors. Water has a high heat capacity. We bring in cool water. It rotates around everything. It picks up the heat. It allows for rapid heat loss. And then the heat from that water is generally going to turn the water into steam. The steam is then going to be used to turn the turbine, to run the generator, to create the power. So the heat, some of it is lost, but a lot of it is going to be transformed then into electrical energy. But not all of the water, well, not all of the heat can be taken out of the water. Because like 75 degrees Celsius water isn't going to turn anything. It creates no steam. It's still hot. One of the biggest waste products that we get from nuclear power is hot water. Because they have to do something with it. So they will have a way of cooling down the water, but eventually they need to get rid of it and bring in more water. You'll find that many nuclear power plants are located next to a water source, usually a river. They will put the hot water, that is waste product, into the river. It contains no nuclear material. It is not radioactive. It has just been used to cool the system. And they will remove more cold water from the river and use that to go in. So the water is just kind of like taking a detour through the nuclear power plant. Have you heard of thermal pollution? Some of you have. Thermal pollution is a thing. It is heat pollution. And we find that thermal pollution is common next to nuclear reactors. It's also common next to some wastewater treatment plants where the water is warmed as it is processed. And sometimes it's a good thing. Sometimes it's a bad thing.
Couldn't you have like a water source that's not a natural space?
Some of them do have recirculating systems, but then it costs energy to cool your water down. So that reduces your energy efficiency. Already the energy efficiency is about 25% of the energy is converted into electrical energy. So then if you have to divert some of that to then recool your water down.
I don't know if that's what I was thinking of. I was thinking like if you have like a lake, but it's a man-made lake and not like an ecosystem. I don't know if
You
that,
could.
and then like when the hot water went into it, it wouldn't disturb anything there. I don't know if that's like
You
actually.
could, but that does divert water from the global water cycle.
Okay.
That is then usable to nothing else other than that.
Okay.
So one of the reasons we usually do it like this is that it allows the water to still be usable in the system.
Got it.
So we're not removing, because less than 2% of the water on the world is capable to be used for like human endeavors for fresh water. So we want to not divert any more of that than we already have.
Okay.
And this just takes it for a little bit.
Would it be possible to go and just use polluted water as a source for trying to maintain?
If you couple this with something that would remove the pollution, yes. And if you're certain that your pollutants will not interact with each other as they are warmed to heat and steam, and that they will not destroy your turbines and everything and corrode them as you go through, then sure.
Okay.
You said that there is bad and good side effects of thermal pollution. What is good?
Who was I talking to about the manatees the other day? Was it none of you? Interesting. So manatees love thermal pollution in the winter. They will go near places in the winter where there is thermal pollution because when the water comes out, it's not boiling. It's warm. And in the winter, animals will actually seek out areas where there is thermal pollution because then they don't have to worry about keeping their body temperatures high because the water around them is constantly warm. So we find that manatees, seals, sea otters, fish, and things will congregate around these areas during winter months. You'll also find in a river that that area will not ice over. So it will actually have higher levels of primary production and things like that because there's more sunlight. So during the winter, they're fabulous. During the summer, it adds additional heat stress into the system. So their effects can depend upon the seasonality. And the first time that they recognized that animals were utilizing nuclear power outflow water pipes as a benefit, people were shocked because the idea was, oh no, this is going to be so bad, but they flocked to them because it's warm. Think of it as like, how many of you like to go home when you're done for the day and like cuddle under your like your fleece blanket or an electric blanket or something, like in nice warm pajamas? It's the same type of effect. So the drawback is that during the summer, it is making these areas extra hot. So then it increases the heat stress of the things that live there. If you're mobile, you can move. If you're a sessile organism, you can't move. So you get stuck there. So you will find different types of species combinations of the sessile organisms there. Mussels, some mussel species have a higher heat tolerance than others, so they'll live there when others that were native to the area might not. But our main waste product here is heat. That's a pretty good waste product comparatively. And this is looking at the overall impacts, though, of nuclear energy, because we can't just look at the production of energy. We have to look at the fact that you have to do mining in order to get to the uranium ore. That usually you have to enrich uranium fuel, which is going to cost a little bit of energy. But then you've got to power the reactor facilities, bring in the water. You have to then let go of the water. Eventually, you're going to have to take your spent fuel rods and store them safely for radioactive waste because they're radioactive. And once again, this is where your book talks about it not falling into... Has anyone read this section and been like, the book really is concerned about nuclear war? It comes up a few times, enough that a few years ago, one of the students asked what was the odds of nuclear war happening because of this. And so far, it seems low. These reactors can't last forever. You do have to take them apart. You have to dismantle them. You have to upgrade them. You have to do a lot of work on them. So that costs money and energy too. And we currently do not have a long-term storage facility for spent fuel and reactor parts because the reactor parts also become contaminated with radioactivity. Does anyone know where we normally store them right now? Didn't go through.
Oh, really?
Never went through.
I thought they like filled it up already or something.
Isn't it just like tanks sitting out in the middle of nowhere or something?
Most of it is stored on site at our nuclear reactors in cool water ponds. They're secure facilities, and I'm pretty sure if you try to pull up Google Earth and like look at them, you're not going to find a whole lot of like aerial photography there, because it's one of the places that we kind of like shut down so that people don't know what it looks like. So you can't like plan like how to take it over. Which is really good. I'm pretty sure my research group is going to spend tomorrow now trying to figure out whether or not this is true. Yes, Elizabeth is shaking her head. She absolutely will look at it for you. So there are some pros and cons of nuclear power. There's a pretty good list of pros and cons. As a matter of fact, I think both of them are great lists. A pro, it's an abundant supply of electrical energy if we can use breeder reactors. So those are ones that are going to allow us to utilize the further breakdown products, so not just uranium 235, but also to use its daughter atoms in the breakdown pathway. We're not really there yet. We can reduce our dependency on foreign oil and on oil in general, which is then going to decrease our production of pollutants from that. There's a low radiation exposure for people that are there. Additionally, if you work at a nuclear power reactor, you have to wear like radiation badges and radiation sensors where if there's a problem, you will know. So they will know if there's going to be a leak. Environmentally, it's mostly clean. Even the mining operations are better than coal mining. It's considered a safe energy supply and it produces absolutely no carbon dioxide. Cons. Uranium itself is not unlimited. So this is only good as long as we have uranium. And we do have enough to last us a long time. But this is not going to be a forever in eternity source of power. It can replace oil in some things. You are never going to drive a nuclear-powered car. It can't happen. It does release radiation if there's a meltdown. It isn't entirely environmentally clean. There's mining, there's thermal pollution, there's the waste that we don't know what to do with because eventually when we do bury it, it's going to contaminate with radioactivity the area where it's taken. There's a safety risk, not only for the employees, but for people who live near them. Does anyone live near 3 Mile Island?
That's super fun.
It's our local nuclear reactor. I had a friend in grad school whose father worked there. She remembers sometimes in the middle of the night phone calls to come in and double check things because there's that fear if something goes wrong and this melts down, lots of people are going to die.
Where is that exactly? Yeah.
It's a little bit south of Harrisburg on the Susquehanna.
Is it like? Do you know where the City Islander Stadium is?
It's like farther down the river. It's like more outside the city.
Okay. So it's probably closer to me.
It's like, it'd be bad. You're in like Brooklyn, right?
Yeah.
It would be bad.
Well, yeah, I know it's bad. I'm just wondering where it is. Because like, is this still running?
They have like, I think they shut down like 2 of the reactors.
Yeah, it's not running at full speed.
So they're still putting.
They did have a partial meltdown at one point,
Yeah.
but no radiation was released. Not even the workers' house was put at risk.
What does a meltdown mean?
We will get there.
Okay.
So there's construction and mining of this that also do produce carbon dioxide. So while nuclear power itself produces no carbon dioxide, the work to get it does. It's expensive. And the public in general is terrified of nuclear power because nuclear. If you could call it uranium power, I feel like people would be on board with it. Nuclear power makes them think nuclear bomb, lots of death. Terrorists. Exactly. Bad things. And then there's 5 major problems. It has a low net energy yield. I told you it was about 25% of the power went from nuclear power to electricity. Some of our other sources that we've looked at are in like the 80% yield. So this is really low. There's safety concerns. Not only for the people working there, but for the community in general.
Is the net energy yield really low because they can't because so much of when they do it, it goes off as steam, I guess, and doesn't go to powering a turbine? Why don't they just? I don't know, this is gonna sound really.
They don't have an
silly.
efficient heat trapping system
Okay.
that would allow them to trap it all and utilize it all. And then low quality steam isn't going to do things as well as high quality hot steam. And then there's the fact that once it transitions back into water, it's useless.
Can you just clarify what the difference between low quality and high quality steam is?
As it's going back towards water droplets forming.
Okay.
So when it's partially condensed, it's not as useful as when it's full steam. Does that make sense?
Yeah.
Long live radioactive waste. What do you do with it? The waste needs to be safely stored for 10,000 years. You know how you don't like it when anyone asks you what your 5-year plan is? Imagine if somebody was like, so what's your 10,000 year plan? Pretty sure for all of us it includes dying.
Yeah,
But-
over 90% of that.
And it needs to be cooled for 5 years before it can even be potentially stored to get it down to a safe storing temperature. We have no reprocessing facilities in the United States for uranium waste. None. We store it in water tanks. The plan was to store it in Yucca Mountain in Nevada. We spent $10 billion, thank you U.S. government, $10 billion on developing this plan. We abandoned the plan in 2011. There were some concerns about Yucca Mountain's proximity to fault lines and potential other problems. They were trying to find a place that was deep enough, remote enough, far enough underground that wouldn't have contamination of like surface water or groundwater or other things. And it fit all of those, but then there was also a consideration that there was no good way to like secure it, and what if there was a problem, and would, not that an earthquake would affect it, but would, if something happened there, cause massive earthquakes elsewhere and massive problems. Because if this blows up, imagine like a nuclear bomb like a mile under the earth. there are potentials for problems there.
Wasn't it also just like too small? Like
Yeah,
they had
it was
too
not.
much
It was
support?
one of those things where it would work in the short term, but it also wouldn't work for 10,000 years. So we currently have no long-term storage. Big, big con. The only reason nuclear power is as cheap as it is because of tax breaks and government subsidies. Replacing these systems is highly expensive. The upkeep on them is highly expensive. And then there's the risk of terrorist nuclear weapons. There's a lot of nuclear, and for that matter, dirty. The idea of making dirty bombs, this is like the perfect material for making a dirty bomb, if you've heard that word before. Because it's already partially broken down, it's going to be easy to use, and, well, nobody's really keeping tabs on... We're keeping tabs on it in the cooling pools, but it's not like you stole uranium-235, so it won't be necessarily as easy to track with other mechanisms that we currently use for tracking that. It's not going to decrease our dependence on oil. So it is not the magic answer that we thought it was. There are some massive health effects from radiation exposure. What do you think happens when you're exposed to radiation? I'm hearing the right answer.
You get cancer.
You can get cancer. If you're exposed to enough of it, you will die instantaneously. You're exposed to radiation sometimes, I imagine. If you've ever gotten an X-ray or a CAT scan or something like that, you've been exposed to radiation. If you've ever had like a contrast dye with radiation, then you've definitely been exposed to radiation. You've had it in your body. But it depends upon your age, the tissue type, and all sorts of things like what the effects will be. We know that radiation causes genetic mutations because when we're trying to look at genetic mutations in other organisms, we induce mutations by using radiation. Most studies done on radiation exposure have been done either from people in the Chernobyl area or the people of Japan who we bombed during World War II. There's very limited studies on this because we only have a few instances of nuclear exposure. And it made it very hard for researchers in the US to study people who we had effectively caused the health problems in a good, objective way, or for that matter, in an ethical way. And 3 Mile Island is 10 miles from Harrisburg, approximately. There was a meltdown there where, well before any of you were born, a valve did not close properly and radioactive steam was released. Hydrogen gas built up. There was a threatened meltdown. It never happened, though, because they were able to prevent it and change the way the system was set up. They had people there watching it all of the time. That's how this works. There are 24 hours of people at nuclear power plants. They're never left humanless to control. The core melted down. And what does that mean? It went through this fast, uncontrolled nuclear reaction where it got so hot that it literally melted the metal and everything in there. So meltdown is actually dealing with melting of everything. That reactor, gone. Okay. Compared to a few other things, it's kind of a minor problem. It was a human error. There was a mechanical failure, a design flaw because the thing didn't close. Lost about $1 billion on this. And suddenly the US population lost its confidence in nuclear power. Because if this can happen, especially so close to Philadelphia, DC, and New York, how good is this for everyone? Chernobyl happened on April 26, 1986. Are you familiar with Chernobyl? It's a disaster. Considered the biggest nuclear disaster. They were testing their 4th reactor. core melted down entirely. And so much so that it was not contained that it started to explode. 56 people died, which is remarkable. Somewhere between 9,000 and over 200,000 people died from exposure to the radiation over their lifetime. You might wonder that that's a really large span, 9,000 to over 200,000. Part of that has to do with what you consider radiation exposure, and part of it also has to do with lack of cooperation from the Russian government. The fuel rods, actually in the notes, they say that the people saw them glowing red. You should never, ever, ever see the fuel rods themselves glowing red. If so, disaster is imminent. Because that means they've gone through them. The metal is glowing red hot. Imagine the heat with that. They used limestone, lead, clay, boron carbide, and sand to put out the fire. All of that was uncontaminated by nuclear waste. It happened April 26th, but the Russian government kind of kept a lid on the fact that what had happened. It was known that something had happened across Europe, but no one knew what was happening until Sweden recorded high levels of radiation on April 29th, and people started looking into it. Because everyone is kind of thinking at this point in time, well, nuclear power is going to be the way to go ahead with things. And the US and Russia and Europe and Russia hadn't been on happy terms. We just made it through the Cold War, all these other things. So keeping the lid on the fact that they were having a nuclear disaster was really important. People died. There were lots of burns, radiation poisoning, evacuation. As a matter of fact, no one can actually go in still to the nuclear power plant itself. They evacuated all of the towns around it, and just recently have they started reopening the area for people to go back and visit, but not the nuclear power plant. Over 20 countries received measurable radiation, and we have no idea what the long-term effects of it are. So if you want, this is big, the one you're familiar with. In Japan, the Fukushima meltdown, which really wasn't a meltdown, was it? What caused it? Tsunami caused it. It's not a good system. And I'm going to point out, I have a friend who does nuclear power. There's 23 plants in the US similar to the Fukushima one, where if we had a tsunami, we could be equally impacted. And he says in nuclear power that one of the things that people are most afraid of is water, particularly the ocean, because it's unpredictable, which is what I personally love about it. So this happened on March 11th, 2011. There was a tsunami because of earthquakes offshore. And a tsunami, for those of you unfamiliar with it, is a massive wave of water coming at you. But they're unpredictable. You cannot link tsunami size to earthquake. There's no equation that allows you to link them. We knew it was going to happen, but you didn't know how large it was going to be. The flooding destroyed their coolant system, so they could not cool the nuclear reactor, which you're already realizing is bad. They had 2 reactors and spent fuel that was being long-term stored that were damaged, yeah. 1 core did melt down due to a lack of cooling system. There was partial meltdown in 2 others. No one knows how much radiation was released. They really couldn't measure it. The systems weren't equipped to work during a massive wall of water crashing through them. The plant was poorly designed, sure, but once again, we have 23 plants like that in the US. But it wasn't designed for a massive wall of water hitting it. It was also an old plant that needed some repairs. We have recorded radiation in the ocean even still that is from that. It was just a few years ago that the radiation in the ocean reached the west coast of the United States. It's going to take a long time for it to go away. We expect that not only will people have effects, but that the ocean and the animals living in it will have effects. That there will be increases of tumors and other cancers in fish and mammals from this. This is what it looked like afterwards. And this is what our storage facilities look like. So that's the cooling pond and then long-term storage. All right, so what do? What do we do knowing all of this? How do we move forward with power? What do you think? We need, well, one, we need to evaluate the different types of energy sources and see which ones are best, which ones give us a high net energy yield, which give us more benefits than they give us risks, and which ones have benefits that outweigh the costs, both monetary costs and then environmental health and health costs. So you can't just weigh health and environment, you also have to weigh. So our first thing we can do to keep using the same energies we're using right now is just reduce our air pollution emissions. If we reduce air pollution, we're in pretty good shape. Sounds lovely, right? So there's two ways to do this. The first one is called control and cleanup, where basically you know, okay, I'm going to have pollution, I'm just going to clean it up when it's done and control what I can. The second is that we can prevent it or reduce it in the first part. Prevention is always better than cleanup. In the long run, prevention is cheaper than cleanup. In the short term, cleanup is cheaper. So it's going to depend on what type of economic model you picked to evaluate it. And we'll use an example of an oil spill. Which do you think is more expensive, to clean up an oil spill or to build a better boat that holds oil? The second one, building the better boat is way more expensive than cleaning up a small oil spill. What is more expensive over a long period of time? Building better boats or cleaning up lots of oil spills? Building better boats. So that's that idea of control and cleanup versus prevention. And it depends upon what type of thing we bring into it. Both of these methods are pursued through regulation. And if you want to talk more about the regulations with this, you should take environmental regulation and policy next spring, the companion course to all of this. And this is showing you the control and cleanup and prevention options. There are lots of different ways we can do this. And most of the things that you'll see that we do today are control, but some of them are prevention, like using low sulfur coal. That right there is prevention. Improving vehicle fuel efficiency is prevention because it means you're using less gasoline. We can reduce air pollution emissions through the plants themselves. The older plants don't necessarily have to meet the new standards for air pollution that the new plants that are built have to. Congress is not really raising our mileage standards in the US like it's being raised elsewhere. So cars are not being forced to be more fuel efficient. One of the ways that we reduce air pollution is a method called cap and trade. It's also called emissions trading. It means that we say, okay, everybody can produce 100 tons of this air pollutant. Every plant gets a permit for 100 tons. Cody's plant only produces 25 tons. He can now sell or trade his extra 75 tons of pollution to the rest of you so that you can pollute more. Cody makes money, but there's also an incentive then for you to produce less. And with cap and trade, the amount that everybody's allowed to have continuously decreases. We can also reduce our carbon dioxide emissions themselves because carbon dioxide is leading to climate change. We do know that. We need to reduce our carbon dioxide emissions. There's a lot of energy that's wasted. 43% of the energy that is used goes to waste. We can also shift from high carbon dioxide to low. And then there's dealing with nuclear waste. This is how Yucca Mountain would have worked. It doesn't. We really don't have a disposal agreement yet. It's pretty clear. And it's difficult to reprocess it and dangerous to reprocess it into another form of fuel. Our concept for the longest time was underground. That didn't work. There is a current plan. It's not a plan. There's a current idea that we should send it into space, but there's some problems. Not the least of which is if that space shuttle blows up, you have just created a large, large nuclear bomb. So I would like to point out, space is not good. Bottom of the ocean, not good. Affects us and food we eat. So how are we going to deal with it? We can also need to deal with old nuclear power plants. The reactors degrade over time, and all the pieces they're made of are contaminated. The core metal starts to become brittle. As it does, it increases your risk of having a meltdown. Things crack. They fall apart. Repairs are difficult. And in the US, we have a lot of reactors that are getting old. We don't know what to do with them. A study from the Associated Press in 2011 found lots of problems with different plants that we hadn't expected to find, like clogged water lines and leaking valves that don't put anybody at risk for exposure, but also decrease the effectiveness of the power. Currently, when our power plants don't work, we just kind of shut them down and leave them in place. It's not the best method, but this is an example of one that's being decommissioned here. And decommissioned is the process through which it is shut down and no longer used for making energy. It says danger. There is kind of controversy about nuclear for the future. It's better than coal, okay? But it can't do everything. So it's not this miracle fuel that at one point in time we thought it was. There are new ideas of how we can do new power plants. They're not really working yet. Then there's this idea of fusion. Fusion is a great concept. I love fusion as an idea because fusion is going to produce absolutely no waste. Fusion is where we're going to take two forms of heavy hydrogen, deuterium and tritium, and we're going to fuse them together, and we're going to make helium, and it's going to give us power. This is brilliant and safe. And helium is neutral. It doesn't work. We can't make it work. We have spent a lot of money trying to make it work, and we have failed miserably. And we can't control it. So even if we could start it, it's not something that we can easily shut down. You will not have a fusion car. But there's little chance of explosion, so people keep going for it. Fossil fuels are then going to need to be used for many years because we don't have a great alternative right now. I want you to pick what's your best fossil fuel, which for our purposes today includes nuclear. What's the best one? Anyone? Want to pick? How many of you say oil? Anyone for tar sands or oil shale? Natural gas? Coal? Nuclear? Okay, we have an almost unanimous choice of nuclear. I think those of you that didn't are going for natural gas. There are pros and cons for each of them. I'm going to talk you through it. I've already done it. So then, renewable energy. But before we do that, we're going to pick a renewable energy source. Who wants to pick hydropower? No one. Who wants solar? A couple of people. Who wants wind? A couple of people. Okay, let's see. So we have hydropower, and these are reviews we've already talked about. Solar, wind, biofuels. I didn't offer you that one as a choice. Because right now it's not perfect. So what else? No, next time you guys are going to get that slide. How else can we fix this? Because we're almost out of time, but we're almost done. So we can save energy. We can increase energy efficiency. That's a really easy way to do more with less fuel. We believe that with no new technologies, if we just redid how we utilize energy, the US might be able to save about half of its oil and 3/4 of its electricity by just doing things better. turning your lights out, things like that. And if power plants could use high quality heat to do electricity and low quality to heat the buildings, it would actually allow them to save a whole lot of energy. Technology, we could have variable speed motors. Do any of you have a variable speed motor in your car? No. Think about how a bike works, the 10-speed bikes and things where you use different speeds for different ideas. What if we could do that with our engines? What if we had more efficient lighting? LEDs are way, way better than the halogen lamps. Recycling. Scrap steel cuts the use of electricity by 75% for producing steel. Pepsi used to have on their cans years ago that we use just under half the world's petroleum. It's bad because we have really inefficient vehicles. We get 35 miles per gallon. We're hoping to get 54.5 miles per gallon in 2025. I don't think it's going to happen. In China, they're about doing equally bad. Other places in the world have much higher MPG requirements for their cars. What if we did mass transit instead of other things? What if we all had hybrid cars or all electric cars that were affordable? What if fuel actually cost what it should? Does anyone know how much a gallon of gas costs in Europe right now? $15, you think? It's probably somewhere around 8-ish last time I checked. How many of you would drive less if gas cost like $5 a gallon? You would do all of your errands at the same time. We would rethink the way that we do our lives. If you've noticed, SEPTA, FedEx, UPS, things like that are starting to get hybrid and electric vehicles that they're starting to use. And we could ship freight more efficiently. We don't do it efficiently right now. I'll fully admit I'm guilty of that with my Amazon Prime. Not efficient, but it gets me things tomorrow. This is looking at the concept of hybrids. Heating efficiency. What if we made sure the heat stayed in your house? One of the easiest things to do is to put like cling wrap around your windows to keep heat from seeping out. Making sure we have good insulation, making sure you have windows that have a double pane of glass, that have air in between them. For that matter, getting shades for your windows that have little pockets of air that help insulate can decrease house heating costs. Saves you money, but it decreases your use of electricity. Your book says wind is best. We'll see. That's where wind is good. Okay. In the next 30 seconds, find a partner. Pick an energy source. Or do you want me to randomly assign you partners and send you energy sources? How about this? Send me the name of your partner.